Our final speaker of the session, William, senior undergraduate student at Urbana-Champaign, advised by Deepak Vasisht. Research focused on satellite networks, as we'll see today, of course, content delivery, and cloud systems. He's currently working on real-time communications as well. Welcome, William.
Okay, health probe. Okay, it works. Thank you for the introduction. Hello, everyone. I'm William from UIUC, and today I'm going to present our work, StarCDN. This is a joint work of UIUC, Akamai, and University of Massachusetts. By the way, two other authors, Ramesh and Aryan, also sitting here. They are brilliant. Feel free to grab any of us for any questions. In the past decade, the number of satellite launches per year is growing exponentially. This marks humans' access to space has become easier than ever before. With these opportunities, companies like Starlink, OneWeb, and Amazon are building the next generation ubiquitous internet access using low Earth orbit, or LEO satellites. Among them, the largest service provider, Starlink, has more than 7,000 satellites covering almost every inch of the world. It serves 4 million users with a speed more than 100 megabits per second. In 2024, Starlink serves more than 50 petabytes of traffic to just marine-type users every month. As more and more users are joining the LEO network, one natural question to ask is, does existing internet infrastructure work for these satellite users? In particular, I'm going to focus on content delivery networks, or CDNs. It is designed to reduce the cost of delivering content and improve network performance. CDN, it works by deploying countless edge servers all around the world to cache and serve content from a location that is proximal to the users. Since the edge servers are close to the user, the latency is usually low, and one content only needs to be fetched once for multiple deliveries to save WAN traffic. However, recent work shows that CDN does not work super well for satellite users, and let me tell you why. Currently, LEO satellite operates in a bin-pile architecture. What it means is that a user connects to a satellite, which in turn connects to a ground station, and then the ground station connects to an edge server of terrestrial CDN. When the user wants to get some content, say friends, the content will be retrieved from terrestrial CDN to a ground station, send it to a satellite, and then eventually to the user. You may find a small problem here. For every bit of content, you need to fetch again and again, back and forth from Earth and space, which means even though this CDN is literally sitting right next to me, you have to go all the way to the orbit and get it back. So we don't really get the latency benefit of using CDN. There is another problem. The uplink between ground station and the satellites is shared by many users and is a bottleneck. Starlink spends a huge amount of time to try to get more bandwidth from FCC because these resources are just precious. When users are requesting the same content, all of them must be fetched from the Earth. This means even though the edge CDN has cached the content we want to fetch, I still need to send all of them using the uplink and use the downlink, of course. This places a huge burden on the uplink usage, so I don't really get any bandwidth efficiency by using CDN for our satellite links as well. So we lost the second benefit. I was trying to use CDN to get both latency benefits and the bandwidth benefits, but unfortunately here I didn't get any of those. So what can we do here? Our idea is, why not just throw the CDN to space? This is actually not that crazy. More and more companies are just building storage and computational equipment over satellites. And in fact, modern satellites are just flying computers. This can bring back the benefits we wanted. By placing a cache server on the satellites, if the content is in the cache, we can just deliver it to these users and the latency will be low. If it's not in the satellite, we can retrieve it from a terrestrial CDN and save a replica in the space cache. In the future, when multiple users are requesting the same content, we can directly deliver them from the space so that we don't need to fetch again and again using uplink. This is great, and today I'm going to describe exactly how we do that by StarCDN. And in StarCDN, we deal with 3 main challenges. I'm going to present them one by one. The first challenge is content duplication, and let me explain what it is. For optimal service, Starlink used a very dense deployment, as shown in the previous talk. It comprises thousands of satellites. At any time instance, a Starlink user can have more than 10 satellites in view. So if I'm a Starlink user here, I will have more than 10 satellites I can connect to. But at any time instance, I only get to connect to one of them. And this is decided by a global scheduler, which maps users in a region to satellites, while accounting for weather and load balancing conditions. What's really interesting here is this mapping changes very fast to keep it up to date with the satellite motion. For Starlink, this mapping can change every 15 seconds. What this means is after 15 seconds, I may see a completely different mapping schedule. What does it imply for caching in space? This means for the content that's going to be served to these users, they must be available in all satellites because link can change anytime. If we actually do that, it further means we are basically duplicating the same content over and over again over a bunch of satellites that are very close to each other, which is very bad because the storage capacity in space is very, very precious. So to solve this, we try to figure out an idea to pool resource storage together and form some kind of a cluster, so that we can use techniques like consistent hashing to reduce duplication. And just like clusters on the Earth, we also need some kind of high bandwidth communication mechanism between servers in a cluster. And this is enabled by intersatellite links, or ISLs. Let's take a look on the Starlink topology. Within the same orbits, satellites are connected by intra-orbital ISLs, and between different orbits, satellites are connected by inter-orbital ISLs. According to Starlink, these links are quite stable and with a bandwidth more than 100 gigabits per second, gigabits per second, which is even greater than the bandwidth for the first 2 generations of Starlink satellite for Earth to space bandwidth. With this, we can form cluster of a satellite and apply consistent hashing. From high level, consistent hashing is a technique to divide traffic into several buckets and map buckets to different places. We also do that in StarCDN, where we hash requests and map a bucket to different satellites. About how to place bucket and the number of buckets, we have a detailed discussion in our paper, but I'm going to skip the detail in my talk. I'm going to give an intuitive illustration using 4 buckets in a grid pattern. So I color them in 4 different colors. I'm going to repeatedly assign buckets to satellites until every satellite has 1 bucket to serve. Now, let's assume I'm a user who's trying to get the content that's hashed to the color yellow. If they're lucky, they will be connected to a yellow satellite, which in that case, they will be served directly. If they are not lucky, they will be connected to some other satellite, say a purple one. In that case, the serving satellite, the purple one, will hash the request and redirect the traffic to the yellow satellite. And the yellow satellite is actually going to serve the content. By doing so, the yellow content don't need to be duplicated again in the purple satellite. Even though the user request change or the link are rescheduled, the consistent hashing can still find the correct satellite to serve the traffic. So this approach will allow us to optimize the storage capacity utilization by systematically aggregating traffics. The second problem is a drastic access pattern shift caused by orbital motion. In terrestrial CDN, edge server usually serve the same location at almost all time, so it doesn't really see a lot of drastic access pattern change, or at least no random access pattern change, which is not true for LEO satellites because it moves super fast. It moves as fast as 8 kilometers per second and serve a given region for less than 10 minutes. Here is the footprint of one Starlink satellite. As you can see, at 9 minutes, it's serving New York City, but just 15 minutes later, it starts to serve London. One may ask, how different are access patterns and what's the implication here? To quantitatively answer this, we start from New York City and gradually increase the distance to include 9 cities all over the world using Akamai's production trace to see how traffic changes. And here's our result. On the x-axis, we have the distance from New York City in kilometers, and on y-axis, we have the percentage of overlap. Even within US, the percentage of overlap for objects dropped to around 50%, and the overlap for traffic dropped to 80%. As we move out USF, things change completely, and the overlap for both drops significantly. Even for English-speaking metropolitan city like London, the overlap is still very low, which means if we move a cache that used to serve US to London, we'll have very poor hit rate and performance at the beginning. With such drastic asset pattern change and the high mobility of LEO satellites, placing cache server over satellite will be a huge challenge. So to address this, we are trying to find the access pattern one satellite is about to serve and flow the content accordingly. More importantly, we want to do this in space so that we don't need to waste the precious uplink. The most important question to answer is where is the important information or useful information? Here are two satellites going back and forth in the same orbits, and I color their serving range into different colors. Let's take a snapshot around 15 minutes apart. You can see at t equals 0, the blue satellite were serving almost exactly the same region the orange satellite is serving right now. What it means is, from orange satellite's perspective, its next neighbor in the same orbit. We're serving this region I'm serving right now, which contains very useful information. So with this in mind, all we need to do is to ask your neighbor before going down to the ground. So if the request resulting in cache miss, the cache server is going to send a query to the neighbors who might have the content because they were in the same location a few minutes ago. This effectively creates a flow of popular content in the opposite direction of orbital motion. But there are some trade-offs here. At least for the Starlink topology, the distance between satellites in the same orbit is much larger than the distance between satellites in parallel orbits. So it's more latency friendly to fetch from your neighbors in different orbits. Surprisingly, your neighbors in different orbits also has very, very useful access pattern you can utilize and relay fetch from. But I will leave this part of the detail to our paper. Now, let's look into the evaluation of StarCDN. To evaluate this kind of work, we need traces all over the world, which is pretty hard to find because these informations are quite sensitive to companies usually. So to satisfy our and the research community's needs, we enable high-fidelity synthetic trace generation. There were past works on how to build synthetic traces from a production trace with high fidelity. Building on top of this, we present SpaceGen, which is the first tool to make it happen for multiple traces from multiple locations. From a high level, SpaceGen takes several production traces as input, and our statistic extractor is going to extract a footprint descriptor for each trace, which captures information like object size, number of access, and hit rates. Upon this, we also capture a global correlation, which encodes how objects are accessed between different traces. Finally, our algorithm will generate synthetic traces that will mimic the performance of the real trace. We want to briefly highlight the result of our generator. So on the left is the CDF of object spread, which is the number of traces and objects exist in. So if Game of Thrones is very popular, that exists in all 9 traces, it's going to contribute to a spread of 9. Essentially, it's just a metric for correlation. And as you can see, the 2 curves between real and synthetic traces are very close to each other. And on the right, we have aggregated request hit rates over varying cache size in gigabytes. And again, the difference is very small. Now, with traces, we can finally discuss the evaluation setup for StarCDN. We generate 5-day-long synthetic traces from Akamai's production traces. We have around 2 billion requests and 2.5 petabytes of traffic. We use Microsoft Cosmic-based simulation with a cache player. And we simulate for 5 days using Starlink's Generation 153 inclination constellation, and by collecting the latest TLE to predict orbital motion. Here is the main result of our work, the byte hit rate of over cache size in gigabytes. Here, the x-axis is gigabytes from 0 to 100 gigabytes. And the orange curve here represents our baseline, which is placing LRU over satellite directly and nothing else. Our work, StarCDN, has a maximum of 15% byte hit rate improvement over our baseline. And at the cache size of 100 gigabytes, we can save up to 80% of uplinks thanks to its high byte hit rate. We also plot the optimal curve, which is the ideal case of placing cache over satellite, but there are no orbital motion at all. This is impractical, but I'm just going to show the gap here. We also evaluate our own different traffic classes. So here is the high-level result. We have 10% improvement for the website traces and 27% improvement for the download traces. We also have various results, like ablation study, latency, bucket set trade-off, et cetera, in our paper. I encourage the audience who are interested in to read our paper to find this out. So as a conclusion, we're presenting a novel CDN architecture that optimizes satellite network user experience and satellite link utilization by consistent hashing and relay fetch. We also open source the SpaceGen, which is a tool to help you generate multi-traces from multiple locations with correlation. If you're interested in our code and data set, feel free to scan the QR code and check it out. With this, I will conclude the talk today, and I'm happy to take any question.
Thank you. I imagine there's going to be a couple. Okay, yep.
Thank you so much. It's a wonderful talk. One question, comparing with traditional consistent hashing, it seems we still need some duplicate kind of content to be cached in the star locations, right? Do you know what's the quantitative kind of redundancy in terms of caching?
Yeah, that's a perfect question. The redundancy, you can still say it's pretty high since we are using 4 buckets, but we have 1,000 satellites. But it's inevitable because the satellite serving range is very small. So if you use small buckets, of course it will reduce redundancy. But that will mean for you to get to the correct buckets, it probably will need more hops. So with 4 buckets, you need maximum 2 hops to get to the correct server that will serve your content. But if you use more, hops will be more, which means local cache miss and redirect latency will be very high. In our study, 9 buckets using Starlink topology is already very high latency penalty.
Thank you. Last question. Why you used byte hit rate? Because I thought you care more about the latency, so object hit rate seems to be better in the metric.
We also have object hit rate in our paper. It's just I present the byte hit rate since it's more directly correlated with the uplink saving, which is also a main source of result we are claiming for.
Awesome. Thank you.
Oh, question over here.
Yep. Thanks so much for the great work, Jörg from TUM. For one, I'm just curious on how much storage you actually assume to have per satellite. I'm not sure I caught that. And my other question is, you spoke about moving content counter to the satellite motion direction, which is of course perfectly fine, but your Earth also rotates, so how are you going to intertwine this with moving from one orbit to the next? Because after some time your orbit that was previously covering the US will be over the Atlantic or Pacific or whatever. So I'm just curious on how that works.
So the first question is how much storage space, right? We don't know a very precise number that how much Starlink can support right now, but for Earth observation tasks, gigabytes of storage is not very rare to see these days. So for regular CDN edge server, it usually comprises TBs of storage usually. So I don't think it's a very big problem to deploy on satellites. And for second problem, I'm not sure I fully understand it. Do you mean when trajectory shifts, we can utilize
Right, your trajectory drifts because the Earth rotates, and then of course your preceding to succeeding satellite content motion isn't enough.
You mean using links between different objects?
Yes. Between different adjacent orbits on the same...
That's perfect observation because that's what we use in our work. I give the intuitive way of fetching back and forth because it's very easy to understand. But in our work, yes, we use that. Very good observation.
Good, thank you.
Okay, I'm going to make one comment just for the room because I think there's some implications here. You can imagine this isn't the first, but there are some really interesting things going on, and the traffic generator is, I think, a lovely contribution as well. There is an implication to doing this, however, which is it turns every satellite into, effectively, the web server, the connection termination. So what does that mean if the object is not in the cache? Does that mean you're reaching out to the origin, for example? Are you somehow passing off the workload somewhere else? When the satellite falls out, do you have to do some version of a socket migration, which we know is very hard? Then there's another piece as well. Does that mean the satellite company is the CDN? Is there a multi-tenancy model where you allow many to, right? So I think there's a lot of implications. Yeah. All right. That closes the session. Thank you very much for joining, especially. We'll see you soon.